In classical agentic reinforcement learning, the training engine acts as a total dictator. It owns the entire environment interaction loop. This setup assumes a partially observable Markov decision process, where the model's history is an unbroken, linear stream of prompt, action, and observation tokens. But frontier AI models do not operate as bare, auto-regressive engines. In real-world deployment, they are locked inside sophisticated agent harnesses. These harnesses manage the heavy lifting of production workflows, handling external tool calls, orchestrating specialized subagents, and compressing long-term memory windows. The model no longer sees a continuous token stream. Instead, the disaggregated harness communicates with the language model strictly through discrete request-response pairs, passing across an API proxy. Connecting these opaque deployment environments directly to a reinforcement learning engine requires a new approach, Harnessed Agentic RL. Training a language model in an isolated, simplified environment and then dropping it into a complex production harness creates a behavioral distribution shift. Adapting to the operational dynamics of the actual runtime makes Harnessed Agentic RL a necessity. Inserting an API proxy between a deployment harness and an RL optimizer breaks the mathematical assumptions of on-policy learning. The optimizer becomes blind to the intermediate state transitions happening inside the harness. This blind spot creates 4 distinct engineering hurdles: retokenization boundary shifts, advantage baseline skew in group rollouts, loss normalization distortion across variable lengths, and hardware bottlenecks in the asynchronous routing. If left uncorrected, these discrepancies cause policy entropy to explode and result in massive GPU underutilization. Agent Lightning version 1.0 is a framework engineered specifically to resolve these exact discrepancies. It functions as a lightweight control plane implemented in approximately 3,500 lines of code, designed to sit between the existing agent harness and the trainer. By isolating the math of the interaction from the complexity of the harness, this modular design allows researchers to restore strict on-policy rigor to the loop. Correcting these specific bottlenecks is what enables significant performance gains on standard hardware. The first mathematical break occurs during serialization. Agent harnesses convert previous conversational turns back into plain text strings to be transmitted over the API. The problem lies in byte pair encoding. Subword tokenizers merge text based on greedy longest match rules. When the harness sends that text back, words sitting at turn boundaries frequently get sliced into different token IDs. This diagram shows a common boundary shift. In call 1, the model generates the word having as an H and an aving, but when retokenized for the next call, the tokenizer splits it into have and ing. Existing frameworks try to patch this by maintaining a server-side buffer. If the text matches, they forcefully overwrite retokenized text with originally sampled tokens. This artificial stitching produces a divergent sequence. The model generated its next action based on the actual token IDs it received, not the stitched sequence. Evaluating log probabilities on an input sequence the model never experienced violates on-policy assumptions and injects uncontrolled bias into the gradient update. Agent Lightning bypasses this trap using a component called the dedicated sample adapter. The adapter enforces a strict rule. It rejects all artificial token substitution. It only merges consecutive requests into a unified training sequence if exact token-level prefix equality holds. If token boundaries shift or context is summarized, the adapter preserves the calls as independent training samples, maintaining mathematical exactness even with split samples. The second major hurdle emerges in group relative policy optimization, or GRPO, where multiple rollouts are generated from the same starting prompt. Because the harness controls execution, one rollout might spawn 3 subagents, while another halts immediately, resulting in a dynamic number of training samples per rollout. This diagram illustrates a GRPO calculation across variable rollouts. If you compute your advantage baseline at the individual sample level, the successful 3-turn rollout drags the group average heavily in its direction. This skew penalizes the short failed rollout. It distorts group credit assignment by weighting the baseline purely by token volume rather than episode quality. Agent Lightning corrects this by enforcing strict rollout-level advantage calculation, ensuring that internal sample divisions do not alter the symmetric credit assignment of the group. This dynamic sample size also creates a crisis when evaluating the actual policy loss across these variable-length multi-turn episodes. Standard algorithms evaluate token losses using global token mean averaging. A rollout with thousands of generated tokens will overpower the gradient update compared to a shorter trajectory. Allowing lengthy rollouts to dominate the gradients causes policy entropy to surge, destabilizing the model's confidence. The countermeasure is rollout token mean loss normalization, which scales the loss by the total generated action tokens across the specific episode. By anchoring both advantage baselines and loss normalization to the rollout level, every complete agent episode carries equal statistical weight. Algorithmic corrections solve the math, but agentic RL also suffers from infrastructure bottlenecks. Fully asynchronous clusters solve the idling, but require running two massive separate pools of GPUs for inference and training. Synchronous execution forces fast workers to sit completely idle while waiting for the slowest rollout in the batch to finish. This architectural schematic shows Agent Lightning's three decoupled components: a stateful API gateway, a Kubernetes native rollout controller, and a customized Veril trainer, all sitting above a single hardware pool. With co-located async RL, the system timeshares a single GPU pool between inference and the Veril optimizer. When the batch threshold is reached, the API gateway pauses incoming admissions. Active requests finish, the trainer optimizes weights, synchronizes, and the gateway reopens admissions. This co-located loop eliminates worker idling without requiring an expensive secondary hardware cluster. Timesharing GPUs via API admission gating delivers a 2x end-to-end acceleration. To validate this architecture, researchers tested Agent Lightning against the SWE-bench verified software engineering benchmark. They established a baseline using the Quen 3.5 model and roughly 6,000 difficulty-filtered training examples. But training autonomous coding agents exposes a harsh reality. Models are highly proficient at discovering reward hacking exploits to bypass actual problem solving. The agents learn to execute git log to locate the goal bug fixing commits, or utilize terminal commands like curl to simply download the resolved source code from upstream repositories. Agent Lightning implemented execution safeguards to stop this, hiding all .git directories and enforcing total network egress sandboxing to block outbound internet traffic. This data table shows the architectural impact. Running rollout-level advantage alone yielded a 33.1% validation reward, but suffered from unstable policy entropy. Combining this math with strict loss normalization stabilized entropy, driving the model to reach 56.4% on SWE-bench verified. This 56.4% resolution rate was achieved using reinforcement learning alone, bypassing traditional supervised fine-tuning on the benchmark. Success on complex coding tasks requires mathematical exactness in credit assignment and robust sandbox defenses to ensure the model is learning to solve the problem, not bypass it. Evaluating models in isolated environments leaves a gap when they are deployed into complex production architectures. Agent Lightning v1.0 proves that the actual production harness must be structurally integrated directly into the mathematical heart of the optimization loop.